Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing our investigation of mathematical proofs and mathematical logic with a discussion and investigation of counterexamples. Now, counterexamples hold a special place in mathematics, partially because it's always fun to show or explain to somebody why they're wrong, partially because in the process of providing a good and cleverly constructed counterexample, a lot can be sort of learned about things that are true, things that are not true. There's a lot to be gained through the process of building counterexamples, as we'll see. Also, to be honest, counterexamples are probably one of the most applicable parts of mathematical thinking to other disciplines, as we'll talk about in just a little bit. So let's get started first with just a brief discussion of what exactly it means to construct a counterexample and why we would even want to do that. So oftentimes in mathematics, showing a statement is untrue can be just as enlightening as proving a statement is true. So it's definitely one of these situations where there's a tremendous amount to be gained if you make a mathematical statement that is true and know how to prove that it is true. But there is often a lot to be gained in the work to show something is not true. The things that you might gain there is a deeper understanding of why something is not true, the assumptions that might need to be added or the conditions that might not be added to make the statement true, or just an understanding, a deeper appreciation of the underlying structure of whatever branch of mathematics you're looking at. So to show that a mathematical statement is false, we often use what we call counterexamples. A counterexample is simply a specific example where the given statement does not hold. What you want to do is you want to contrast this with what we've been doing if you've been watching these videos in series in what everything else we've been sort of learning about proof techniques. So what we want to contrast here is that when we prove something is true, we're doing this in general. That's been the sort of big thing that we've been reminding you of throughout all of this sort of proof sequence. Whenever you're doing a proof, regardless of whether or not it's a direct proof, proof by contrapositive, contradiction, induction, doesn't matter the technique, you're always proving the statement in general. You're not allowed to prove just through a specific single example or anything like that. You need to show that whatever that statement is, it is always true. But we want to contrast this with the fact that when we want to show something is false, then we do want to give a specific example. So when we prove things are true, we try to do this in general, but when we show something is false, we try to give a specific example. Now, also keep in mind that finding counterexamples, as we sort of mentioned earlier, not only demonstrates why the given statement is untrue, but it can also help us understand what additional assumptions would be necessary to make the statement true. So again, when we think about this, a lot of times counterexamples are viewed as demonstrating why a particular statement is incorrect. But keep in mind, from a broader perspective, by demonstrating why that statement is incorrect, you're probably going to learn a lot about why exactly it's incorrect, what would be necessary to fix the statement, and the underlying structure of the mathematics you're examining here. Lastly, keep in mind here also, why do we even need to give counterexamples when somebody makes a false statement? Well, keep in mind that in mathematics, we don't want to turn things into arguments or opinions, right? If somebody makes a mathematical statement that we know is incorrect or that we think is incorrect, well, they need to either prove that the statement is true or we need to demonstrate an example where it's untrue. We don't want to base this off of I think it's true or I feel like it's untrue or something like that. We either want to have a logically thorough and justified proof that whatever that statement is always true, or we want to have that specific example demonstrating a situation where the statement is untrue. So the counterexample is, in some ways, the other side of the logical coin of mathematical proofs, because it's demonstrating concretely that we know this statement is not always true. Now, before we get into some specific mathematical statements and sort of talk about the art of constructing a counterexample, I want to just give a little sort of discussion, just a very basic example about what it even means to give a counterexample. So, imagine this really bold, clearly incorrect statement. Somebody comes around and says, all dogs are brown. And they're going around there saying every dog in the world, in the universe, however you want to view it, is brown. Now, you might say, that's ridiculous, that's crazy, that's not correct. Okay, all those are fair statements, but if this person is adamant that every dog is brown, the only way that you're going to convince them otherwise is to give them that specific example, to actually show them that dog that is not brown. So notice that a valid counterexample here would be finding a single dog. It can be a specific singular dog that is simply not brown. So if we go out and we find a black dog and we show it to this person, that is our valid counterexample. If we find a white dog and we show it to this person, that is our valid counterexample. That will demonstrate that not every dog out there is brown. Now, what would be an invalid counterexample? Well, here's an invalid counterexample. If we go out and we find ourselves a black cat or a white cat or something like that, some cat that's not brown, that's an invalid counterexample. That's because we didn't follow the assumptions of the statement. This person said all dogs are brown. They didn't make any sort of statement about cats or other animals. So if we're going to provide a counterexample, we better make sure we bring a dog. We have to follow the assumptions of their statement. So when we get into the examples in just a few moments mathematically, we're really going to make sure that we always adhere to the assumptions of the statement. Our example has to satisfy the initial assumptions of the statement. Okay, what else would sort of go wrong? Well, imagine we go out and we say, okay, we know we're looking for a dog. We're not going to bring them a cat or a bird or anything like that, but we're going to go and find a dog. And maybe the first dog that we encounter happens to be a brown dog. So if we happen to find a single brown dog in our investigation, that doesn't mean anything. Just because we've encountered that dog, that doesn't mean that we've proven that their statement is correct. This is just a particular example where the statement holds. It doesn't prove that it's always true. That means we just need to look for another example. So if we're out there looking for our dog, our counterexample here, and the first one we encounter is a brown dog, that doesn't mean anything. We look at it, we say, okay, that's a situation where their statement was right, but we're going to keep going and keep looking for other examples, other dogs, until we find one that is not brown, and that is our counterexample. So I like to mention this here because as we sort of talk about the art of constructing mathematical counterexamples, keep in mind that you might at first stumble into some examples or situations where the proposed statement is correct, right? Where it does hold. That doesn't mean anything. Don't let that discourage you, right? Continue to look for other examples. You just need to find one particular example where the statement doesn't hold. If you find some other ones along the way, that is totally okay. Now, we also mentioned before we get into the mathematics of these counterexamples and some actual sort of mathematical statements, we said that this is one of these sort of situations where this type of thinking is really applicable to other fields. And I would like to just spend a moment to mention this. The idea of building counterexamples or thinking of counterexamples, it's a type of thinking where we're looking at a general statement that might either be like this, really obviously incorrect, or maybe one that looks really, really sound, looks almost true. Either way, our goal in some ways is to try to break that statement, to try to figure out what is the weirdest, craziest situation we can sort of subject the statement to that might actually invalidate it. And in a lot of other disciplines, say like computer science, that's a really important type of thinking. If you're constructing, say, an algorithm or something, there's a concept called corner cases, where your algorithm might apply to the vast majority of basic situations, but maybe it doesn't apply to certain bizarre initial starting conditions. That type of thinking is the same as building a counterexample to a mathematical statement. Same thing if you're imagining designing, say, a business or a workflow. Maybe you have a particular business or you've designed a workflow for some task and 90% of the time it runs just as you would imagine. But again, maybe there's some unique initial situations or unique things that can happen throughout that workflow that suddenly break this nicely designed great idea that you have. Those, once again, are in some ways counterexamples to whatever your general idea, your general approach was. So the better you get at designing mathematical counterexamples, the more comfortable you'll be thinking about what things can go wrong in whatever sort of field you're looking at. And that type of thinking is really beneficial for understanding not the majority of cases, but understanding those unique situations where things are a little bit different, where we have to be aware of how that can sort of throw off what we might think normally or generally works. All right, so without further ado, let's get to some actual mathematical statements and actually see how to construct a counterexample. So here is our first mathematical statement. This guy says that if we have 4 distinct numbers, then 2 of them are below the average and 2 of them are above the average. Now remember, just really quickly, average just means that we would add up all the numbers and divide by the amount of the numbers there. So it's saying if we have 4 distinct numbers, then 2 of them are below the average and 2 of them are above the average. Now again, depending on your comfortability with like statistics and things like that, you might feel like, wow, this sounds sort of true, or you might be a little suspicious about it. Certainly this is something where if somebody said this, it would be tough to say, well, no, you're just wrong, without sort of really giving them an example, right? There's some amount of where this seems reasonable, then it really requires us to give a concrete example. Now, if we do this, right, we have to keep in mind that, and we're trying our example here, we have to adhere to this fact that they said 4 distinct numbers. So as we do this, right, if we try to come up with our example here, so we'll put our sort of counterexample, right? And we'll call it a counterexample attempt because we don't really know if we're going to come up with a counterexample on our first sort of thing. Let's just try to think of 4 distinct numbers. Now, of course, we know we're going to have to add them up and divide by 4, so let's pick things that are easy. They have to be distinct, so maybe we'll just have our set of numbers be 2, 4, 6, and 8, right? Those should be very easy to add. If you're constructing a counterexample, stylistically, there is no point, at least initially, of making it really complex. If you think about it from a style point or a rhetoric point of view, if you're trying to convince somebody that they're incorrect, it's probably better to give them a nice, simple, easy to follow example of why they're wrong than something that's really convoluted. Now, if it requires a lot of complexity to break their statement, then that's all we can do. But at least we should start at a relatively sort of simple point. So we've got our 4 numbers there. We can sort of check, right? The average here would just be 2 plus 4 plus 6 plus 8 divided by 4. And that looks like 6 plus 6, 12, 20 over 4, which is 5. And then if we just sort of imagine this value of 5 here, 5 would be sort of right in there. And, well, 2 of the numbers are less than 5. 2 of the numbers are bigger than 5. And unfortunately, that is what the statement says. 2 of them are below average. 2 of them are above average. So we picked out an example where this statement was true. That means this isn't going to help us in terms of constructing a counterexample. So while this was a good example of the statement, right, this right here, not going to be particularly useful for us. Okay, well, that doesn't mean that the statement is true. That's just one particular example where it happened to be true. Well, let's try something else then. Let's try a new counterexample. If we think about it, we don't want to do something super similar. We don't want to, again, do like, we shouldn't shift it to 4, 6, 8, 10, because that seems basically the same mathematically. We could say maybe we should introduce maybe we shouldn't do like whole numbers. Maybe we should try like negative numbers or something. We could certainly try something like that. Or we could just try a very simple change. We sort of had all the numbers close together. Let's have one of them be a lot different than the others. So what if we did something like 2, 4, 6, and then instead of 8, we just did 80, right? So something where instead of having all the numbers grouped together, we choose them to all be very sort of different. Okay, if we do the average here, we have 2 plus 4 plus 6 plus 80 over 4. And that looks like it's going to be 6 plus 6, that's 12, plus 80, that's that 92 over 4. And that sounds like, that's going to be 23, right, when we do that? I think so. Okay, so the average is 23. If we look at that, that average now would be like here between those numbers, right? So that 23 would be right here. We're having just a bit of issue with the stylus. One moment. Sorry about that. We'll have that going in just a second. Okay, and there it is. There's our 23. And we can see that 3 of the values are less than that, 1 of the values is greater than that, and that is our counterexample, right? 3 values are less than the average, 1 value is greater than the average. So this is our counterexample. That demonstrates, right, that we don't have a situation, right, and this is a situation where we do not have 2 of them being below average and 2 of them being above average. So that is our counterexample. That shows that we cannot say in general that if you have 4 distinct numbers, that 2 of them are below the average and 2 of them are above the average. We've given a counterexample. We've shown that that statement does not always hold. There will be certain situations, like our first example, where it does hold, but there will be other ones where it doesn't. So the main takeaway from this first example is, first, if you happen to come up with an example and the statement works, that's okay, right? Just try something else. And the other thing is to treat this as something where you just simply try to play around with it, right? As you do more and more counterexamples and this type of thinking, you might develop a better sense of how to start off constructing your example, but at least at the beginning, just try to make sure that you adhere to the assumptions, try things out, and then change things based on whether or not, if that example didn't work, then keep trying other things. So let's go ahead and take a look at another example here. So in this one, it says if f of x is continuous, then f of x is differentiable. So once again, when we do this, we're going to have to think of a specific example. We're going to have to make sure our function is continuous. And then we have to find something where it's not differentiable. Now, this one is a lot more mathematically written. I just want to go back quickly to the other one. The other one was written out a lot more sort of in English. And so it was very clear that our goal was to have one where it wasn't 2 below the average and 2 above the average. Sometimes in something like this, where it's written a little bit more mathematically, keep in mind what we can sort of make a little note of what we want, right? We sort of want f of x continuous. So we want to follow that assumption, but f of x not differentiable. So again, sometimes this is sort of similar to the thinking of like a need to show, right? This isn't really a need to show because it's not a general statement, but it's a reminder of what our goal is, right? We have to adhere to the fact that it's supposed to be continuous, and then we're supposed to break the second part, right, that says f of x is differentiable. So we're going to show but f of x is not differentiable. Now, depending on our Calc 1 sort of knowledge, we might remember sort of what visually continuity and differentiability mean. Continuity sort of means that we can draw it without having to sort of lift up our pen or pencil, or in this case, our stylus, since we're doing this on a tablet. And differentiable means that you can do that smoothly, meaning that there's no sharp corners. So notice that that makes it very easy to come up with a visual counterexample to this, right? A visual counterexample to this would be simply drawing something, right? So we'll draw ourselves an axis, and then we'll draw our function, right? We'll just have this sort of, doing whatever, going like this, going like that. All that's continuous and differentiable. Then let's have it, the stylus is doing funny things there. Let's just draw that. Let's have it go like that. And then let's say it gets to there. And then right there, let's put a sharp corner, something that's non-differentiable, something like that. So maybe our curve does something like this, right? So we've constructed a sharp corner right here, a place where it'll be non-differentiable. Now, some people would say, you know what, that's good enough. If you have a good understanding of continuity and differentiability, you will know that the fact that this was drawn without having to pick up the sort of pen there, right? I should make sure that when I do it in the laser here, right, we can sort of see that this is a sharp corner there, right? Is that guarantees it's continuous, right? Since we can do that all in one motion. And then the fact that that's a sharp corner there, that means it's non-differentiable. If you wanted to elaborate on the picture, you could say, with a little bit of sort of zooming in, that clearly, right, if we sort of used some colors to annotate, we could say that over here, right, slope is clearly negative, right? Because it's downward, right? It's moving down there. But over here, slope is positive. But here, right, slope is not equal to 0. So since it transitioned from negative to positive without going through 0, it must not be differentiable, right? That could be a little bit more of an explanation onto our diagram about why it's non-differentiable there. Now, some people would say, okay, I believe the diagram, that's good enough. Some other people would say stylistically, well, I don't want to just base it off of a picture. I want an actual function. I want an explicit equation for our function. So we could come up with a different counterexample. Remember, these statements, there's the potential where there's many, many counterexamples. So we can always develop another one. So let's try a different one where we actually use maybe a simpler picture, similar idea, but one that we know pretty well. A famous continuous but non-differentiable one, a famous sharp corner sort of picture is your absolute value function. So this right here is your absolute value function, right? This would be f of x equals absolute value x, or if you prefer, this is f of x as a piecewise function, negative x when x is less than 0, x when x is greater than or equal to 0. And clearly, this guy is continuous, but f of x not differentiable at x equals 0. Now again, probably most people would say, okay, that's sufficiently convinced. I don't need to really have anything more demonstrated. But if you really wanted to, you could sort of know, right, that f prime of x is equal to negative 1 for x less than 0, right? It's always negative 1 slope because it's linear over here. And then f prime of x equals positive 1 for x greater than 0, but f prime x does not exist for x equal to 0. And that would be further justification. Again, it really depends on like the level of formality that maybe the situation, or for a lot of people as students, the sort of class dictates whether or not you would be sufficient to just simply draw a picture with some annotation, an actual explicit function, an explicit function with some extra annotation. Either way, though, we've demonstrated several counterexamples here where we had a continuous function that was non-differentiable. Okay? Now, this also is a good example because this is a reminder of how you can also gain some knowledge, or remember some knowledge more likely in this situation, while you're doing this. You might be looking at this and saying, well, I sort of remember that there is a relationship between differentiability and continuity. And as you're doing this, you're reminded that the direction that would make this statement true is if it was written in its converse. If f of x is differentiable, then it must be continuous. And that was a one-directional statement. If you know a function is differentiable, then it must be continuous. But what we've just shown is that the converse of that true statement is not true. That if f of x is continuous, then f of x is differentiable. This tells us why in a Calc 1 class, they show us, or they tell us the theorem, f of x is differentiable, then f of x is continuous, but they don't say this statement. And that's because it's not true. So again, even though we were just doing this as a problem, just trying to sort of practice coming up with a counterexample, along the way, we're reminded of our knowledge about this area of mathematics. And we're reminded that if the statement was reversed, it would be true. And now we also know why people don't use this direction of the statement. It's because it's not true, as demonstrated by our examples. Okay, let's move to another one. So here we go. We've got an interesting one here. If f of x is strictly increasing and continuous, then the limit as x goes to infinity of f of x approaches infinity. Now this, I think, is a great example because initially, if we're sort of thinking about this, right? So I'll just make a note. This is just some thinking. I think what most people would do is they'd say, okay, strictly increasing and continuous, so I've got to sort of draw it like that, right? I can't have any sort of gaps or something, and since it's strictly increasing, it's got to go up. So people would normally think, they would draw something like that, and they'd say, well, that looks problematic because as this is going, it seems to be going up and up, which is saying that the limit of f of x approaches infinity. So you can see how this statement is one that might seem sort of true. It might seem believable. Now, we're doing this as a counterexample practice, so we sort of know that maybe something isn't true, and this is what sort of requires us to have that sort of counterexample thinking, that counterexample mindset of how can we break this. So let's see if we can do this first visually, just like we did in the previous one, and then we'll try to come up with an explicit function. So let's give ourselves sort of an axis here. We're going to do it continuously, so we're going to draw this in sort of one motion. So here's our function, we're drawing, we're coming up. But instead of having it sort of increasing in terms of its speed, concavity, as you would call it in Calc 1, let's have it start to taper off, but still going up, something like that. Now I'm going to redraw that just a little bit because the sort of cursor took over, but we're going to have something that's sort of doing something like that. Now, this guy is still going to be going up as we're here, so it's still increasing, but it's going slower and slower. So this is something where we have an increasing but concave down curve. Now, what we're making happen here is we're having an asymptote, a horizontal asymptote coming across here that this curve is approaching, right? That means it's getting closer and closer to it. That's what's ensuring that it's strictly increasing. But whatever this asymptote value is, that's the limit, right? Whenever this is here, right, we can clearly see visually that the limit as x goes to infinity of our f of x function, it's approaching whatever that limit, whatever that asymptote is, which is clearly not positive infinity. So this would be a valid counterexample, right? I mean, if we draw a continuous curve and it always stays below this horizontal asymptote, clearly it's always increasing, it's always going up. It's just that the rate of increase is getting less and less, and it's going to stay below that limit of L, that horizontal asymptote. That's going to be its end behavior. That's not positive infinity. That's a counterexample. Again, this to me would be a totally sufficient way of sort of explaining it. It definitely justifies strictly increasing and continuous, and clearly it shows why the limit is not going to positive infinity. Perfect. If we do want to be sort of specific, we can try to come up with an actual explicit function here. So another counterexample, if we want, right? We could try to come up with one, think about something that sort of does this. We could think about something, say, like 1 minus 1 over x, right? Something like that. That would have a continuity issue at like x equals 0. So what we could do is, if we just want to ensure that we don't have any continuity issues, I suppose we could just go ahead and do like an x squared plus 1 down there instead. That would ensure that we're continuous. If we don't like that, or if you want something maybe a little bit easier, we could just go ahead and do like an exponential function there, which won't have any continuity issues. So we could do like e to the negative x or something like that. Now, again, how would we justify this? Well, now we can, since we actually have an explicit function, instead of drawing the graph, it's probably a little bit easier to show that this is strictly increasing. Well, since one way to know strictly increasing is you can use the definition. If you put in a larger input, you get out a larger output. Another way you can do strictly increasing is by looking at the picture like we did here, or you can use some calculus knowledge, look at the derivative. F prime of x here is e to the negative x. And notice the exponential function, no matter what exponent you put into it, is always positive. So this is always greater than 0. So your derivative is always positive. That means you are strictly increasing. Okay, so it's strictly increasing. But if we do the limit here, x goes to infinity, 1 minus e to the negative x. This approaches 1 minus e to the negative infinity. Remember, Don't write any sort of equals here, right? Because you're just approaching. You can't be equaling infinity or anything like that, but you can use that arrow to say it's approaching. This right here, that e to the negative infinity, that's going to be going very, very close to 0. As you put in massive negative exponents into the exponential, it approaches 0. So this approaches 1 minus 0, which is equal to 1. We didn't need it to equal 1, but equaling 1 certainly doesn't equal infinity. And that tells us that we have achieved that. So we know we have something continuous. That's pretty clear because all these functions are continuous. A little bit more justification for why it's strictly increasing using the derivative. And the end behavior, in this case, approaches 1, which is certainly not positive infinity. Like you saw, you could do something like 1 minus 1 over x squared plus 1. You could come up with other examples as long as you ensure the continuity, as long as you ensure strictly increasing, and as long as you can demonstrate that the limit is not approaching positive infinity. So again, this is a good one where we had a couple conditions to check or to satisfy, and we can again do it from a visual standpoint, or you can be a little bit more explicit and actually come up with a function. All right, let's turn to our last one, which is one that requires sort of us to really think outside the sort of box, and also will be a good discussion about what we can gain from this type of thinking. So for our last one, we have a function that says if f of negative 1 is equal to negative 1 and f of 1 equals 1, then the function f of x equaling 0 has at least one solution. Sorry, then the equation, excuse me, f of x equals 0 has at least one solution on negative 1 to 1. So this is basically saying that if our function is at negative 1, when you plug in negative 1, if it then gets to 1 by the time you plug in 1, that it must cross the x-axis, or the function must equal 0, somewhere between negative 1 and 1. Now, for some of you, if Calc 1 is relatively recent, you might read this and say, well, that sounds really true, right? I mean, if we sort of imagine, if we're down here at negative 1, 1, and we're up here at 1, 1, when we draw this thing, no matter how we sort of draw it, it always seems to cross the x-axis, f of x equaling 0, at least once. Obviously, it could happen more, right? I mean, we could have here, and maybe it does something like that, right? And so then there'd be like here, 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 5 times in my weird picture. But this says at least once, so we're not going to break it like that. Well, if we go back to all those pictures we just sort of were drawing, right? We're saying we're here, and I was drawing it like that. Or if I draw it like that, or like we said, if you try to get fancy, you go up and down, none of that is going to sort of help us. So at first we might say, well, I don't really see visually then how we're going to break this thing. But if you consider it, when we did all those pictures, right, we were sort of implicitly, just because we're sort of used to it, always drawing continuous curves, right? When I was drawing this point to here, we're always sort of drawing it in one motion without picking up our sort of pen. But notice there's no statement of that here. It never says to assume that f of x is continuous. So if we can't break it with continuity, that means we need to break it when we don't have continuity. So notice that would make a very easy visual counterexample where we could simply have a function, right, where maybe it's down here at minus 1, and this is positive 1 up here. Maybe this function goes along like this, right, down here. Then right when you get to 1, put yourself an open dot, jump up here, and then continue on, right? Now, clearly, right, it satisfies f of negative 1 equals negative 1. That's right here. It satisfies f of 1 equals 1. That's right here. So it does what we want it to do. But notice, f of x equaling 0 has no solutions because it never hits the x-axis, and it certainly doesn't hit it from negative 1 to 1. So this would be a great counterexample. Now, if you do want an explicit formula for that, an explicit equation, wouldn't be hard to write out the piecewise thing that we just did, right? Good skill to have to be able to write down a picture and then translate it into a function. Most of our mathematical careers we've done the other way, given a function, draw its graph, but we can do the other way as well. this would be simply -1 when x is strictly less than 1. That's why we have an open dot there. And then 1 when x is greater than or equal to 1. And that's why we have a solid dot there. That would be an equation for this graph, and that would be a great counterexample. Now, notice when we did this, not only did we break the statement showing why it's not a true statement, we also realized that it would be a true statement if they had the assumption of continuity. In fact, if we had the assumption of continuity along with these two assumptions, then we would be able to use what you learned in Calc 1 as the intermediate value theorem to say that since f of x is continuous, and since it is at -1 and 1, it must cross through 0. That's what we call the intermediate value theorem. But since we didn't have that assumption of continuity, then we were able to come up with our counterexample. So you can think about this in a couple different ways. You can say to yourself, if a theorem seems like it would apply here, well, think about the conditions of that theorem, and if one of those conditions is omitted, then use that condition, break that condition, and that should give you your counterexample. It would be true with continuity, so we made up an example without continuity. Or, if you prefer to think about it after the fact, you can sort of say to yourself, this is why continuity is necessary as one of the assumptions in that intermediate value theorem. If we don't have that continuity assumption, then examples like this would be possible, and we wouldn't be able to draw those types of conclusions. So all of this has been just a quick discussion of counterexamples. Just like all your proof techniques, counterexamples are something that are only going to really make sense or feel sort of comfortable to you with practice by just trying to look at mathematical statements and build your counterexamples. So I really recommend you try practicing the idea and creation of counterexamples. Remember, always try to start simple with them. There's no reason to make really difficult, complicated examples, at least at first. Remember also, the more complicated your example, the more work you need to do to demonstrate why it satisfies the assumptions and why it breaks the desired conclusion. So simple is better here. Pictures are great. Understanding theorems that would have applied if there had been other conditions can also be tremendously beneficial. Hopefully this has been sort of an interesting discussion here, and we'll catch you in the next video.